My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. So, good morning to all here in Bangladesh, and a very good evening to all those who are watching this program live from USA. So, as we know that we are staying in a corona pandemic situation, so it's very difficult for us to continue our normal academic program inside the campus. So, I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar, and we are trying to adjust with this new normal situation, and we have successfully completed our 142nd International Physics Web, and today it's our 143rd. And today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, University of Pittsburgh, USA, in Physics and Astronomy. And we have with us here today Dr. Chandralekha Singh, Madam, Professor, Department of Physics and Astronomy, founding director of the Discipline-Based Science Education Research Center, University of Pittsburgh, USA, and she has already connected with us. So I'd like to welcome our speaker. So good morning, Madam, and welcome to our International Physics webinar. And thanks for accepting our invitation. So for those who are new, I'd like to inform that we have divided our webinar into three parts. First of all, I would like to introduce our speaker, and then our speaker will deliver her speech. And at the end, we have a discussion session. In that time, anybody can join with us. So I think you have already come to know the title of this today's International Physics webinar. Title is the Facilitating Thinking and Learning in and Beyond the Physics Classroom. Very interesting topic. And our speaker is Dr. Chandralekha Singh, Madam, Professor, Department of Physics and Astronomy, and founding director of the Discipline-Based Science Education Research Center, University of Pittsburgh, USA. We can see her educational and career background. Dr. Chandralekha Singh is a professor in the Department of Physics and Astronomy and the founding director of the Discipline-Based Science Education Research Center at the University of Pittsburgh. She is currently the president of the American Association for Physics Teachers. She obtained her bachelor and master's degrees from the Indian Institute of Technology, IIT Kharagpur, and her PhD in the theoretical condensed matter physics from the University of California. She was a postdoctoral fellow at the University of Illinois. Before joining the University of Pittsburgh, she has investigated superconductivity, self-organized criticality, nonlinear optical properties of conducting polymers at interfaces, transport of ions in ion channel, among other things. She has been conducting research in physics education for 2 decades. She co-led the US team to the International Conference on Women in Physics in Birmingham, UK in 2017. She is a fellow of the American Physical Society, American Association for the Advancement of Science, and the American Association of Physics Teachers. So this is her educational record: bachelor and master's from IIT Kharagpur, and MA in Physics, University of California, PhD, University of California, and the postdoctoral fellow, University of Illinois. Research. The goal of her research is to identify sources of student difficulties in learning physics both at the introductory and advanced levels, and to design, implement, and assess curricula that may significantly reduce the difficulties. The objective is to enable students at all levels to develop critical thinking skill and to become good problem solvers and independent learners. Professor Singh's publication related to physics education research, research on learning quantum mechanics, quantum interactive learning tutorials, research on validated standardized assessment instruments, research on longitudinal assessment, research on technology enhanced learning, research on intuition and expertise in physics, research on metacognition in physics, problem solving, scaffolding and transfer, analogical reasoning, isomorphic problems, role of representation in problem solving, research on TA professional development, research on learning introductory and advanced physics, research on equity and inclusion in physics learning. And this is her award, American Associate of the Advancement of Science Fellow 2018. Carnegie Science Center University Post-Secondary Education Award 2017, American Association of Physics Teacher Fellow 2014, Fellow of the American Physical Society 2012, AAPT Distinguished Service Citation 2012, Chancellor's Distinguished Teachers Award 2002, Ballet Teaching Excellent Award 2000. And this is her recent publication. So thanks for all of your patience. Now it's time to go to our speaker. Madam, I'd like to welcome you again, and it's your time, madam. You can start your session.
So should I actually share my screen now?
Yeah, of course, madam, you can.
Okay, so I'm going to share my entire screen. And wait, did I share my screen or not?
Yeah, I think we can see. Yeah, we can see.
Okay, so you can see my screen.
Yeah.
All right, so I want to actually make sure that you can actually see my slides. So can you
Yeah,
see
I
my
can
slide
see.
now?
Yes, madam. I can see your slide.
All right, so thank you so much, Pretam. And so
Yeah,
I'm
it's a
going to be
pleasure.
talking about facilitating thinking and learning in physics classrooms and beyond physics classrooms. So basically, I'm going to give you some examples of the kinds of research I have done focused on improving student learning of physics. So before I get started on other research, I first wanted to talk about the research related to what does it mean to think like a physicist? Because you often hear about the fact that, you know, we want students to learn to think like physicists. But what is the meaning of that? And one of the things that is really difficult is how do you get faculty or physics professors to actually solve problems that they don't know how to solve? Because oftentimes, the kinds of problems that professors usually give to students are problems about which they already have a lot of intuition. And if you have a lot of intuition about how to solve those problems, then you don't have to think on your feet. You don't really have to do thinking when you're trying to actually solve the problem. And so we wanted to actually see what happens in situations in which professors do not have any intuition about how to solve the problem. And when you ask them to think aloud while they solve the problem, they must do the same kind of thinking that the students are doing, which means thinking on their feet. So this was a study that was done, that was published in American Journal of Physics, and 20 physics professors and a lot of students from introductory physics participated in this. And if you are familiar with the book Halliday-Resnick, that's the book from which we picked a problem. And this is a problem which is at the introductory level, but even then it is non-intuitive. By non-intuitive, I mean even professors have not really thought about how to solve this problem. So they really have to think on their feet in order to figure out how to solve this problem. So let me tell you what the problem is. The problem is that of a spinning wheel that is spinning for some time, and then it falls on the ground, and then it slips for some time, and then finally starts to roll without slipping. And the question is, how does the final speed, v sub f, depend upon how much is the coefficient of friction on this surface, assuming that there is some friction here? Okay, so assuming that there is some friction, if suppose, so my question is this, if suppose the coefficient of friction was larger, would that mean that this wheel's final speed will be smaller, no change at all, or will it be greater than if the frictional coefficient was smaller? Does that make sense? That is the question. So how does this final speed, V final is equal to R times omega final, and this is the speed at which the wheel locks in and it starts to roll without slipping, how does it depend upon the friction on the surface? Now, notice I told you this is a really difficult problem even for physics professors. And the reason is they haven't really thought about this problem, even though it happens to be a problem from Halliday-Resnick. And so, it turns out that the reason it's difficult is that there are two things that are important here. One is how much is the frictional coefficient? The other one is how long does it take for the wheel to start to roll? What we found is, and so if suppose the frictional coefficient is smaller, then it'll take a long time for the wheel to lock in and start to roll without slipping. If the frictional coefficient is larger, then the wheel will lock in quickly, and it'll take a short time before V final becomes equal to R times omega final, and the wheel starts to roll. Now, since these two things are conspiring in opposite direction and it's a really hard problem to figure out, what we did see is that faculty were having difficulty solving this non-intuitive problem on the spot, right? And they only focused on one variable. They were either focusing on friction, or they were focusing on, how much time does it take to roll without slipping. But you could tell from the way that they were solving problems that this problem, that they knew how to solve problems. What do I mean by that? For example, they were thinking about limiting cases. What happens when there's no friction, or what happens when there's infinite amount of friction, right? And that is a really good heuristic, thinking about limiting cases. It doesn't help you for this problem, but it still is a very good heuristic. They were also thinking about like analogies to familiar situations. What happens to the wheels of an airplane when it lands on the ground? How does the frictional coefficient of the surface determine the final speed at which it will start to roll without slipping? Again, this is a really great heuristic. And analogies are really great tools that we should really be helping our students learn. Now, other things that faculty did was some of them even went to the board and drew a diagram. And so, also, they were thinking about doing a conceptual analysis. They were thinking about planning the solution. What am I given? Where am I going? Like, what are the principles of physics that might be applicable here? Can I use some conservation law, like linear momentum, angular momentum, conservation of energy? It turns out that you can solve this problem using the conservation of angular momentum about the point where the wheel first touches the ground, because the frictional coefficient passes through that point. So angular momentum is conserved about that point. Of course, angular momentum conservation is a tricky one because you have to think about the point about which angular momentum is conserved. So it was really hard for faculty to actually solve this problem when they were given this problem, and we were literally sitting there telling them, how would you solve it? Think aloud, talk aloud about how you would solve this problem, right? So we had put them in the same situation that students often are when they're trying to do quizzes or they're trying to do exams. But we also interviewed students in the same way using think aloud interviews, where they were asked to think aloud while they were thinking about how to solve this problem. And we clearly saw that students did not have the same systematic approach that faculty were using, even in this non-intuitive problem about which they didn't have intuition. Now, which means that there was definitely something to be said about what does it mean to think like a physicist. What it means to think like a physicist is that you should be doing a conceptual analysis of the problem. You should be planning the solution instead of just jumping into formula searching. You should actually be thinking about limiting cases. You should be thinking about analogies to familiar situations. You should be thinking about predicting what should you expect in this problem, and then check later on whether you got that or not. You should be actually thinking about principles of physics that might be applicable here and why. The only thing is that in this particular problem, even faculty actually had to think on their feet in real time. So there definitely was difference between the way the instructors were thinking about this and the students were thinking about it. Now, the other thing was that we gave to both students and faculty this other problem, which is a ballistic pendulum problem. And this is a problem that everybody is really familiar with in physics. So this is like about two putties that are actually hanging from a ceiling. One of them is raised to a certain height. You let go, it comes down, collides with the other one, and the two things go up together. And the question is asking, how do you find what principles of physics would you be using to find the final height of the two putties stuck together in terms of the initial height, right? What we found, this is the problem here, like two putties, and this one is raised to a certain height, h naught, goes down, collides with this one, stick together, goes up. And the question is, what will be this final height, h of f, in terms of the initial height? And notice that you need to use conservation of momentum when the collision takes place. And you have to use conservation of mechanical energy to figure out what is the speed of this one right before it hits this one. Then when the two things hit each other, that's the momentum conservation. And then when the two things stuck together go up, that is mechanical energy conservation again. In other words, you have to use both momentum conservation and mechanical energy conservation. As you can see from this thing below, this was given to more than 2,000 students from 14 different universities. And basically, what we found is that only 27% of the students after instruction provided the correct response. And this is like across, as I said, 14 different universities. So after instruction. And the interesting thing was that faculty said that this problem about ballistic pendulum would be really easy for their students compared to that spinning wheel problem. Now, notice that for the students, actually, this problem turned out to be as difficult as that spinning wheel problem. In fact, this is only slightly better than guessing, because if they had guessed with this 5 option question, they would have gotten like, 20% correct. So what it really means is that um, faculty did not really think about the difficulty of this problem from their students' perspective. They were thinking that this problem would be really easy because they could immediately tell that, oh, yes, for this problem, you would use conservation of mechanical energy when this thing comes down to figure out what will be its speed right before it hits this one. Then when it hits this thing, figuring out what would be the speed of the two things stuck together, you'll be using conservation of momentum. And then when it goes up, it's mechanical energy conservation again. And so they were like, oh, this is such an easy problem. But it's not easy because it's really a problem that is 3 parts that are temporally separated, like, things going down, things sticking together, and then going up. And so they are not really thinking about the difficulty of the problem from students' perspective, and they are thinking about it from their own perspective. And this is a huge problem in teaching and learning, because the perceived difficulty of a problem not only depends upon its inherent complexity, but also on the familiarity and experience and intuition you have built about it. So if you are an instructor, if you're a professor who's trying to actually help your students learn better, you should always be putting yourself in your students' shoes and thinking about, will my students find this problem difficult? Not from your own perspective. Like, for example, for that ballistic pendulum problem, you might have a lot of experience and you might think it's easy, but it's not really easy. All right, at this point, I wanted to move on to another research study that we had done. And this research study focuses on what is the role of reflection in physics problem solving. Because when you are actually helping students do problem solving, you want them to use that opportunity to learn. So when students struggle to solve problems and they are actually not getting it right, and only after a lot of struggle when they get it right, we want them to reflect and do metacognition and think about, what were the features of this problem that made it so difficult, because of which I'm not able to do it, right? But the point is that unfortunately, problem solving often turns out to be a missed learning opportunity. What I mean by that is many times students may not actually reflect upon what have they done wrong, what have they done incorrectly, and how can I make sure that I do not make the same mistake again next time when I'm trying to solve the problem, right? So the question is, can we actually deliberately prompt students to use the problem solving as a learning opportunity, right? And by that, I mean, what if we actually rewarded students by giving them certain amounts of like grade back or points back to the students for correcting their own mistakes before we gave them the correct answer to, say, quizzes or exams, for example. And so we have done a lot of studies in this area, and here are the papers that relate to this. Here I'm going to only talk about one study that we did in upper level quantum mechanics course. But we have done also a lot of studies in introductory physics, these ones here. And even in those studies, we find very similar results, which means that if we ask students to correct their mistakes by giving them certain amounts of point back for, say, quizzes or midterm exams, then if you give the same kind of problems later to students in the final exam, you find that students do a lot better than students who are just given the correct solutions to those questions right away. Notice that both groups of students is getting the correct answer to the questions, just that for one group, you're making them struggle 2 times. Like they've taken a quiz or they've taken a midterm exam, those things were under time constraints. Then you said, okay, at this point, I'll give you back your graded thing. You go home and you correct your mistake, looking at your books, looking at your notes, and I will give you certain amount of points back for the mistakes that you've made if you correct it. And then when they bring it back to you, then you actually give them the correct answer. Okay. So basically, I'm talking about it in the case of quantum mechanics, and this is something we published in 2016. And so the question is, do students automatically learn from their mistakes? And this is in advanced quantum mechanics, undergraduate quantum mechanics. So we wanted to see, will there be any difference in the performance of the students later in the final exam if students were not given any grade incentive to correct their mistakes versus if they were given grade incentives to correct their mistakes? Okay. So we did this thing. We gave to students like 4 problems on 2 midterm exams, and then later some of those problems were given in the final exam. Okay, so here are the 2 groups. Comparison group means the group that was not given any incentive to correct mistake, so they were just basically given the correct solutions right away along with their own graded stuff. And here in the incentivized group, students were actually given first some incentive to correct the mistake. So they were asked to take their graded stuff back and then bring it back for some point backs. So they had to correct their mistakes. And then when they did that, then the correct solutions were provided. And when I say pre here, I mean, how did the students do first time around on those 4 problems, right? And you can see all the students together got around 68%. This is low means like the students who didn't do well. Like, so we divided the students into 3 groups depending upon how they had done the first time. And you can see some students did really poorly, some did kind of medium, and some did really well. And here in the incentivized group, it's kind of similar. Notice that, and then at the end of the semester, in the final exam, when students did similar questions, what you find is that the low group actually improved a little bit, but not a lot. Medium group, hardly any. And the high group, of course, they are doing really well. But if you look at this particular incentivized group, you see that this group is doing really well, right? A lot better than here. This group is also doing a lot better here. Of course, this group was always doing well. So you can see that giving incentives to correct mistakes actually helps the students who are not doing well or who are doing kind of in the middle. Okay, so it is a good thing for students for you as an instructor to ask students to correct their mistakes for certain points back, because students will learn much more from that. Otherwise, students may not learn. And in fact, we even interviewed some students, 6 students who had not done well the second time in that comparison group. And we asked them, why did you look at the solutions that the instructor had provided to you? Because if you had looked at those solutions, you would have done a lot better. And students said things like, I don't like to look at the solutions if I do poorly. So I just put it in my book bag and never look back. Or, I don't pay attention to the solutions to the midterm exam because I don't think that those kinds of questions will again show up in the final exam. But notice that these are actually not good reasons for not doing well. And if you give explicit incentives to students to correct mistakes, they are actually going to learn. So at this point, I want to move on to research studies that we have actually done in student learning of quantum mechanics concepts. Okay. So one of the things that we have found is that the kind of difficulties that introductory students have in classical mechanics learning, like for example, in introductory physics, right? People think that if a huge trailer truck hits a small car, then the trailer truck is exerting a larger force on the small car. Of course, this is wrong, right? Newton's third law says that the forces are going to be equal in magnitude and opposite in direction. So, but it's a really hard thing. Similarly, if people think that if an object is moving at a constant velocity, there must be some net force on it, but that is wrong. The net force on an object that is moving at a constant velocity is 0. That's what, Newton's law says again. But these are really hard things because people think, oh, but if a car was moving at 60 miles an hour, there was some force initially to get it moving. So somehow that force is carrying with the car. So there are all these different kinds of conceptions that are incorrect. And it's really hard to actually help students with those concepts. Now, you might think that it's easier for students to learn quantum mechanics because there would not be misconceptions or alternative conceptions about quantum mechanics, because you don't really come across those kinds of things that you learn in quantum mechanics in your everyday experience because you're dealing with microscopic world. But it turns out that that's not really true. And the reason students are having a lot of difficulties in quantum mechanics is that the paradigm of classical mechanics and quantum mechanics are very different, right? So people already have developed very clear notion of what should position mean, what should momentum mean, right? What should energy mean? And so, like, I mean, and those things, position and momentum, those things in classical mechanics are deterministic things. But now in quantum mechanics, they are not deterministic, they're probabilistic. And so, and then, like momentum and position are actually operators that act on states in Hilbert space where nobody can hear you scream. And so the point is that, these are ideas that are so different that students actually start having a lot of difficulty in learning quantum mechanics. So we wrote an article in Physics Today on improving student learning of quantum mechanics. And basically, we came up with a taxonomy of student difficulties in this area. And so I'm going to give you some examples of the kinds of things that we found. So, for example, one of the, and this study was done with upper level students and graduate students even in 9 different universities. And basically, they were asked these kinds of questions. Okay, if suppose you have some kind of a quantum state in which the state of the system is a linear superposition of the ground state and the first excited state like this, right, with these coefficients. The first part was asking about the probability for measuring energy, different values of energy in this state. And you can see that the correct answer would be that 2/7 is the probability of measuring energy E1 for ground state, and 5/7, which is the absolute square of this, is the probability of measuring E2. It turns out 67% of the students provided the correct response, and the ones who didn't often were confused about individual measurements versus expectation value. Also, we asked students about the second part of the same question was asking about the expectation value, right? And you can see that only 39% of the students provided the correct response for the expectation value of energy. Now, notice that the reason this was the second part of the same question was that expectation value is the average of the large number of measurements on identically prepared system. So if you have already found out what is the probability of measuring different values of energy here in part 1 of the question, and here you are supposed to find the expectation value of energy, expectation value is going to be the average of the large number of measurement on identically prepared systems. So it's just going to be 2/3 times E1, 2/7 times E1 plus 5/7 times E2, and that is it. So this part's answer should be just 2/7 times E1 plus 5/7 times E2, because the probability of measuring all other energies is 0. But that's not the way most of the students actually answered the question about expectation value. Most of the students were answering it by actually using a very algorithmic approach, which means they were saying, oh, it is going to be integral psi star h psi, where h is the Hamiltonian operator that corresponds to the energy of the system. So the point is that if you actually write down that kind of an integral and you have like this kind of a linear superposition, and you have to take the absolute, you have to take the complex conjugates of this in psi star, and then you have to use orthonormality, and you have to do the integral correctly for the infinite square well case that this is for. It is from 0 to the 0 to a is the integral limit, not minus infinity to plus infinity or something. So people made lots of different kinds of mistakes, because of which ultimately that algorithmic approach did not give the right answer, and the percentage of students who got the correct answer for the second part is a lot smaller. Because if students had recognized the expectation value in terms of the average of a large number of measurements on identically prepared systems, then they could have just said, oh, I know that the answer would be 2/7 times E1 plus 5/7 times E2. So I'm not saying that there is anything wrong in using an algorithmic approach, integral psi star h psi, but that method is going to lead to incorrect answers often if people don't remember some of those mathematical things and they get distracted by other things. So having students develop conceptual understanding is very important, but we have to do a good job as instructors for making sure that students actually develop a conceptual understanding of expectation value as an average of a large number of measurements on identically prepared systems, all of which are in this state. All right. So another question that we gave to students was about the time dependence of wave function. So this is a quantum state again, and we asked them, what is the state, is the probability density for the state going to depend upon time? And the point is that in this case, it will depend upon time, because you can see that the state phi 1, which is the ground state, the time evolution of this is going to be e to the power minus I E1t over h bar, and this one is going to be e to the power minus I E2t over h bar. And if we look at the absolute square of it, then we are going to get the cross terms, right? And those cross terms will not cancel out. So you will have a time dependence to the probability density, which is really the absolute square of this thing. But we find that only 43% of the students provided the correct response. And oftentimes the most incorrect response, what common incorrect response was saying that the time dependence of the state is just e to the power minus IET over h bar, an overall phase. But that is not correct, because the ground state and first excited states have different energies, right? So the time-dependent phases will have e to the power minus IE1t over h bar, and here e to the power minus IE2t over h bar. So, but again, you can see that students are having difficulty in differentiating between an energy eigenstate or stationary state and a non-stationary state of the system. So that means we found that students were having many common difficulty regardless of the background, teaching style, and textbook, because I told you that there were 9 different universities involved in these studies. All of them were from the United States. And there is a striking similarity in the kind of difficulties that students were having in introductory physics that I talked to you about, like Newton's laws, what kinds of difficulties students have. So the question is, what can we do to help students be able to discriminate between related concepts and not just overgeneralize some of the concepts they have learned? So one of the things is that cognitive science says that we need to really understand the difficulties that students are having and then build on that knowledge, right? And the good thing is that, there are approaches that we can use, pedagogical strategies that we can use to help students learn these concepts much better. And we should not only be thinking about the difficulty of the problem from students' perspective. And we should actually be developing systematic tasks that are consistent with students' knowledge and build on their current knowledge and make it grow. So basically what we are doing is we are actually developing quantum interactive learning tutorials, or QuILTs. And these are based on findings of student difficulties in learning quantum mechanics. They use a guided approach to learning that builds on students' prior knowledge. And hints and feedback is given to students as needed. And these things actually are designed to bridge the gap between the conceptual and quantitative aspects of quantum mechanics. And we use computer-based visualization tools, which are mostly adapted from open source physics simulations, but we also use some PhET simulations and other things. And students are kept actively engaged in the learning process. And each of the tutorial comes with a pretest that you can give to students after traditional instruction, and post-test that you give after students have worked on the tutorial to see how much students have improved after learning from a particular QuILT. So for example, in the time evolution QuILT, the pretest might say, okay, let me ask for the probability density. I've given the wave function at time t equal to 0, and it's looking like this as some linear superposition of ground and first excited state. And I'm going to ask for the probability density in this case and whether it depends upon time or not. And then I'm only going to ask it for, let's say, just the ground state or just the first excited state. And notice that in the probability density, in the case of just ground state or just first excited state, the probability density will not depend upon time, because in that case, you will have the time-dependent phase factor canceling out when you take the absolute square like this. But if you have a linear superposition, then as we discussed, the cross terms will not cancel out, and so the probability density will depend upon time. Now, as you saw, often the common difficulty was that students didn't think that there was a difference between stationary and non-stationary state. So they were kind of not able to really differentiate between those two. So basically, then what the QuILT will do is it will actually um, look at what happened. It'll say to students, okay, why don't you actually look at these simulations? And these are basically time-lapsed pictures. So this is basically X, and this is psi star psi, probability density in the vertical axis. And you can see that this is time t equal to 0. This is a little bit greater time. This is even greater. This is even greater. And you can see that the probability density for this linear superposition of ground and first excited state is changing with time. And so now students are in a state of disequilibrium. You've caused a cognitive conflict because they want to understand, why is this not what I was expecting? And so at this point, the QuILT will go on to help students think about how the eigenstates of the Hamiltonian are special. And that is why, because the Hamiltonian is the one that governs the time evolution of the system according to time dependent Schrodinger equation, IH bar del psi over del t is equal to 8 psi. And so, that's why eigenstates of the Hamiltonian are special. But if you're not in an eigenstate, but a linear superposition of energy eigenstate, then the probability density actually will depend upon time. So you can see here, we have developed a lot of tutorial. These are just a few examples. You can see like Stern-Gerlach experiment is a really nice example with a two-state system. We have things on quantum key distribution, which is very important thing in quantum information science and technology. This is really quantum cryptography is a very exciting topic that many students would love learning about. And what you can see is that after traditional instruction, student performance is not as good, but after they work on the QuILT, their performance becomes a lot better. So if you're interested in using these QuILTs, they're all available on Fizzboard, but you can also email me and I can send you the link. We've also developed these clicker questions, these multiple choice questions that you can ask students in class, and you can ask students to talk to each other. We have developed a lot of these, and these are also available on the website. And again, I wanted to show you here, I'm showing you about infinite square well topic. And if you look at the percentage of students on the vertical axis and what was their score on this topic, these purple things are referring to the case where students only had traditional instruction, whereas these blue things and the yellow things refer to two different classes in which students had used these multiple choice questions to actually learn during the class as clicker questions. But you can also have students just thinking about it on themselves, pairing with another student in the class next to them, and doing think, pair, share, and then there will be a general class discussion about why some answers are correct and some answers are not correct. And so you can see that these two classes are definitely doing a lot better than this class. All right, so at this point, I also wanted to talk about improving students' self-efficacy, their sense of belonging, and their intelligence mindset in introductory physics. So what is the meaning of the word self-efficacy? Self-efficacy is students' beliefs in one's capability to succeed in a particular task, course, or subject, and it can impact students' performance and engagement. And it can also affect, science course performance, even after you control for students' prior knowledge, right? And at least in the we know about physics, for example. Physics is something in which there have been very few women. Like this is the famous Solvay conference from 1927, and you can see that Marie Curie is the only person. All of the other people are men, right? Here is Schrodinger, here is Einstein. You get the point, right? Here is Pauli. So and so the point is that if in this kind of a situation, it's possible that when women go into physics, they're like, oh, I don't belong here. And this is from a recent conference in America. And again, if you look at this doesn't look that different from that Solvay conference 1927 picture. And this is from 2014. And so the question is, in fact, we find in our own university that if you look at this self-efficacy, that means belief about students in how good they are, men have a much higher score on that than women do, right? So, and the point is that this is not a good thing. Like these are the kinds of things that women are saying, I have pretty low self-confidence when I see how other people are so smart. I don't feel comfortable in this class. But for physics, I feel like I don't connect things well. But a lot of these kinds of things are really due to people's self-efficacy and the fact that we are not really making the learning environment very good for women, for example, because they are underrepresented in physics. So the question is, what can we do, right? So one of the things that we did, this is something that has been done a lot in America in high school math classes, and it has really worked well. So what we did was we incorporated a very short intervention that the instructor does at the beginning of the semester, right? And we did it in the recitation class. And we had this intervention is called social belonging and mindset intervention. And so three instructors participated, and some of the recitation classes participated. And by recitation, we mean like, if you have a class with, say, 100, 200 students, they are divided into like 40 student groups. Those are called recitations, in which students work in small groups on problems, right? And they're working collaboratively. And these are basically the classes in which we wanted students to understand that struggling is the only way to learn something new. So they should actually be patting themselves on the back, and they should be proud of struggling, because this means that they are already on their way to learning something new. So they should be proud of doing challenging problems and feel good about it. And the reason this kind of an idea is really important to convey to students is because of a lot of times when students struggle, they have very different reaction. Either they say, it's good, I'm on my way to learning something new. Or they say, oh, it's bad because, I'm struggling maybe because I'm a woman and I'm not good at physics or something like that. And if they get into that kind of a wrong state, then, they become really anxious, and the anxiety takes up their cognitive resources, because cognitive science says that your brain has only like 5 to 9 slots, right? And if some of those slots are being taken up by the anxiety of the situation, you're not going to use all of those slots to do problem solving. And so that is a really bad thing, right? So the good thing about like having this intervention and the instructor saying that you should struggle, even Einstein has said that struggling, that if you haven't struggled, you haven't tried to learn anything new. And so basically, the idea is to reduce anxiety, reduce procrastination, because notice you don't want to do something that you think you're not going to be good at. Increase your enthusiasm for solving challenging problems, and ensure that the limited cognitive resources are used for problem solving as opposed to anxiety. Okay. So the intervention was like this, so basically, the students were asked to actually write on a piece of paper what their concerns were about being in the physics course for the first 10 minutes. And they wrote a lot, and then we told them, okay, stop. And then after that, we showed them testimonials of the students from previous year who actually said that they were very concerned about how they were going to do in the physics course. But then they decided that the thing that was really important was to work hard, work smart, take advantage of all the resources, and work collaboratively with other students, go to the instructor, go to the teaching assistant, and get help from them. And lo and behold, they did challenging problems, they worked hard and smart, and they ended up doing really well, right? And we have some names of women, some names of men. And what you see is that everybody's saying the same thing. And after students see these testimonials from students from previous years who have done really well, then they are told to get together in small groups of 5 and discuss what they wrote on the sheet of paper. And why don't people realize that struggling is actually a good thing? And most people struggle. And we want and what students actually realize in these small groups is that, oh, other people are also having like these worries about how I'm going to do in this course. And that, struggling is actually a good thing. So everybody actually kind of discusses this thing in small groups, and they all come to the conclusion that it's a good thing. Okay. So I think at this point, yeah, this is just an example of what a student wrote in that essay that we asked them to write. Here is like one of the testimonials that we showed, and we also wrote at the bottom some name, like for example, this is Allison. And by the way, some of the students in these introductory physics classes are also engineers, because engineering students also have to take physics. So, and as I said, there was a group discussion, and notice that if there was just that, First of all, women were so happy that we did this thing. They actually thanked us. They said, "Oh, thanks so much for doing this." Okay. But if that was the end of it, we would still have thought that that short activity, which only takes like 25 to 30 minutes at the beginning of the course, one time, to increase students excitement about struggling and doing challenging problems, if that was the only thing, we would still have been happy. But what we see, if you look at the thing, in some of the recitation classes we actually use this intervention, and light blue is men and dark blue is women. And you can see that in the control group, women were doing a lot worse than men when they were having anxiety. But in the social belonging group, the performance of women and men is comparable. In fact, like in we see similar kinds of things in for students who are underrepresented by race, like for example, racial and ethnic minority students. We again saw similar kinds of things if the intervention took place or didn't take place. And I don't want to talk about what happened in biology, but even in the biology course, similar kinds of results were seen. So basically, the idea is that we should not only worry about teaching students efficient problem solving, effective problem solving skills, and transfer their learning from one situation to the other and develop a robust understanding of physics, but we should also worry about defense. That means increasing students' sense of belonging, increasing their self-efficacy, their intelligence mindset, their identity about how good they are, because those things can also increase their interest and their achievement goals about how good they can be in physics. So a short activity focused on belonging actually helped a lot. And we actually are now doing professional development of the TAs or teaching assistants to help with this kind of thing. And some of these ideas also apply in mentoring students. So if you are mentoring students who are women, again, if you don't actually encourage them and if you don't actually say that they're doing well, many a times they won't realize that they're actually doing well, and they might get anxious about things. So the point is that it's really important to validate students, it's really important to affirm students, and it's really important to have them recognize that nobody goes in a straight path. Struggles are common, and struggles are something that we should embrace and use those as a stepping stone to learning something new. So at this point, I would like to stop and take any questions.
Yeah, thank you, madam, for your wonderful presentation and interesting topic also. So we have got two questions in inbox. So that one student actually asked that this data maybe you have shown from US based research. So have you taken any data from South Asia?
No, I don't have any data from.
Okay, another question. So how can we increase the women participation in physics research in our part? Maybe in US it have a large number of women in research, but in our part maybe that number is not that much. So how we can improve? Is
Sorry,
there
how can we improve the number of what?
women participation in research?
Of women? How can we improve participation of women in research? So that's exactly what I'm saying, that like participation of women is really affected by the fact that, first of all, there is not much encouragement for women to do studies in these areas. Secondly, they are not being recognized. So they need to be recognized and supported. So when they are actually, let's say that, like they're making progress, right? The advisor needs to say, but the person that they are working with needs to say, you are doing well. This is good. You're making progress, right? And if they actually like if suppose they are not able to make progress because like research doesn't necessarily go in a straight line, so it's possible that for 3 months, 4 months, you're struggling with something and it's not working, right? You're doing an experiment and it's not working out. Again, the advisor needs to say, this is okay, you need to keep learning from whatever you are doing, so all the things that are not working are still teaching you, right? So the thing is, it's only when you give up then you actually fail. But otherwise, all of those failures that you actually are having are good. Like they are teaching you something about what is not going to work so that ultimately it will work. I remember, like, even in my own PhD research, I remember there were things that were not working from time, but I was always like learning from those. But somebody's PhD advisor needs to actually support them and validate them and make sure that they keep telling them that they are actually doing just fine. And this is typical of how a PhD research actually goes.
Yeah, thank you, madam. So there is the last question from one of my colleagues. So you have mentioned about the mark get back to student after correcting their mistakes. So his question is the what percentage of marks should we need to give back to student after correction the mistakes?
Okay, that is a really good point because in our case, if you read our paper, what you will see is that both in introductory physics and in advanced physics, we always gave 50% of the points back. But, I mean, I know that my colleagues here have been giving different amounts of points. And in America, we have had like many people doing this kind of thing, and they have given different amounts. And I think that whatever you feel is good is fine. So 50% is what we have given generally. But I mean, I don't think that there is a fixed rule, but giving students incentive, great incentive, even if you give a smaller percent than that, it would still be good because students will do something for points for sure.
Yeah, thank you, madam, for your wonderful presentation and discussion session, madam. I think student and the teacher also learn a lot of things from this yeah, very important webinar about the facilitating thinking of learning and beyond the in and beyond the classroom. So thanks again, madam, for accepting our invitation, and we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. So thanks again, madam. And
Well,
it's
thank
our
you so
pleasure.
much.
Yeah, you are welcome, madam.
Thanks. Thank you.
Bye
See
for
you.
today. Yeah, see you.